Hi there. In this video, we're going to be looking at integration of exact differentials. So an exact differential has the form dz is equal to dz dx times dx plus dz dy dy. We want to integrate dz and end up with z. And we saw in the last video, for us to be able to do this, it has to meet a certain test. We have to check if this dz can actually be integrated to begin with. And that check is, we let, firstly, dz dx equal to p, and we let dz dy equal q. And that check was, the derivative of p with respect to y must equal to the derivative of q with respect to x. Once it does meet this test, then this function can be differentiated. So if we just remove this first part of this differential, we just say p dx, right? So this should be z, and this should also be z, because if we add apples and apples, we should get apples, right? So this should be a part of z, and that should also be a part of z. So if you think about z as being p dx, sorry, dz being p dx, then what this means is that z should simply equal to the derivative of, sorry, the integral of p dx. And the same would apply to y. If dz is equal to q dy, then z should also equal to the integral of q dy. So we have two integrals, right? p dx and q dy. And we see that z is equal to both of them. So how do we reconcile this now? Which one is actually z? How do we go about resolving this? So we can easily see that they're the same thing. You're looking at an example. So that example is dz is equal to 2xy plus 6x dx plus x squared plus 2y cubed dy. So as before, we let the first term equal to p and the second term equal to q. So p would equal to 2xy plus 6x, and q would equal to x squared plus 2y cubed. So firstly, we check if this thing is an exact differential. So we find the derivative of p with respect to y, and that's just equal to 2x. We can see, yeah, y to the power 1, so we just left with 2x. And then we find the derivative of q with respect to x. So that would just equal to 2x. So we see that they're the same, so therefore we can proceed. So if z is equal to the integral of p dx, well, let's just write that down. Z is equal to the integral of p. P is 2xy plus 6x. 2xy plus 6x dx. And now we integrate this. And when we do that, we see that we get x squared y plus 3x squared. And then if we do the same with y, we say that z is equal to q dy. So q is x squared plus 2y cubed and we're integrating this with respect to y. And when we do that, we get x squared y plus y to the power 4, and then 4 times something must give us 2. So that's a half. 4 times a half will give us 2. So this is integrated. So there's one other thing that we need to mention here, right? If we look at the original function, since this is a multivariable function, when we differentiate with x, we keep y constant, right? So what we're saying here is that we should have a constant of integration that is somehow a function of y, because if we differentiate y, we get 0, which is exactly what is the case here. And the same must be true here as well. If we differentiate something with respect to x and y is held constant, or rather we differentiate something with respect to y and x is held constant, it means that if some other function was something of x, it had x in it, it became 0 once we differentiated it. So we need to take that into consideration. So here, when we integrated with respect to x, it means that there was some function maybe of y. There was some function of y, and if we differentiated it, it became 0. So that's why it doesn't appear in the integral. And the same is true here. It means that there was some function that had x in it, and then if we differentiated it with respect to y, then it means that it became 0, and that's why it's not in the integral. So let's look at these two results that we have. We have x squared plus y squared, okay? And then look on the right-hand side, we have x squared plus y squared, so they're the same. Now we need to have some function of y. How do we get this function of y? Well, let's look on the right-hand side. Do we have a function of y? Yes, we do. Half y to the power 4. And then again, looking on the right-hand side, we need a function of x. Do we have a function of x that is only of x? Yes, we do. So what this means is that this g that's a function of y should equal to this function on the right-hand side, this term on the right-hand side that is only a function of y. And in the same way, this function of x should equal to this term on the left-hand side, which is only a function of x. What this means is that z, when we combine it, is equal to x squared plus y squared, that doesn't change, x squared y, plus 3x squared. 3x squared corresponds to this function of x, plus the function of y, which we saw to be a half y to the power 4. So there we go. If we differentiate this and find this differential z, we should end up with our original problem, which was 2xy plus 6x, etc. So you could actually do that and just double check it. So in a nutshell, all we need to do is identify the part of the differential that is p, and then identify the part of the differential that's q, and then integrate p with respect to x, as we've done here, and differentiate it with respect to y, as we've done here. That's with respect to x, and that's with respect to y. And once we do that, we just combine our two results, identifying the functions of x and y, and that will give us our original function z. In this video, we're going to be looking at the area inside a closed curve. Let's start off by looking at a closed curve in the xy plane. We draw our xy axis. We have a point A, and that point A has a value of x1, and it's being connected to a point B with x value x2. A is linked to B by one curve. Maybe this curve could be g of x, and B is linked to A also via another curve, maybe f of x. So we could think of maybe a particle that's traveling from A to B and then going back to A via the other curve. So two paths between 2 points. So our task is to find the area inside this closed curve. So the manner in which we would go about doing it is we would find the area underneath the top curve, which is being showed in green, and then we would subtract it from the area underneath the bottom curve, which is being shown in red. So what we're left with is the area inside the closed curve. So we'll just write that down. So we'll let A1 represent the area underneath the top curve, and that's given by the integral from x1 to x2 of f of x dx. And we just want to reverse the order of the integration between the points. So instead of going from x1 to x2, we'll go from x2 to x1. And then we know from our laws of integration, if we do that, if we reverse the path of integration, we need to put a minus sign in front. Why we're doing this will become clear just now. So now we're integrating from x2 to x1, and we have reversed the sign. Now A2 is the area underneath the bottom curve. So that is also from x1 to x2, and that's of g of x. So the area underneath the closed curve, the area inside, that's equal to a1 minus a2, as we have just seen. And then if we write this in terms of the integration, what it would be is the integral of x1 to x2 f of x dx minus the integral from x1 to x2 of g of x dx. So what we're going to do now is we're going to reverse the order of integration as we've indicated here for f of x, and we're just going to put this second term with respect to g of x in front. So we're going to say minus the integral of x1 to x2 g of x dx minus the integral from x2 to x1 of f of x dx. So why have we done this? Well, we have made it look this way because we can now represent this as the path taken by some particle that we were talking about earlier. So imagine that the particle goes from from A to B in the bottom curve. So it goes like that, right? So that would correspond to x1 to x2 of g of x, the bottom curve. Then it goes from B to A by the top curve, and that corresponds to x2 back to x1 of f of x dx. So x1 to x2, then from x2 back to x1. So that's what we're showing. x1 to x2, and then from x2 back to x1. We're just going to take the negative out as a common factor. So what we're left with is the integral from x1 to x2 g of x dx plus the integral from x2 to x1 of f of x dx. So there's just a symbol that's given to represent this kind of integration. That symbol is the integration sign, so we just put the minus there, is a circle. So we would have this minus sign that's in front, and we would have the integral sign, and we would put a circle inside it like that to integrate, to show that it's the integration inside a closed curve. And y corresponds to our two functions, and dx is our variable that we're integrating with respect to. So I think this procedure will be most easily highlighted through a simple example. So we want to find the area between the two curves. Y is equal to x cubed and y is equal to 4x. And the question is, find the area of integration, or find the area inside the closed curve bounded by these two functions. So if we were to just do a quick plot of these two curves, we won't draw the y is equal to x cubed, the complete thing, but there is a portion of the curve that looks like that, and y is equal to 4x is obviously a straight line. So these two will intersect, and we need to find this point of intersection. And what we're saying is that we want to integrate from this point of origin to maybe this point A, and then back to this point of origin. And maybe as part of the question, we should just say that x is greater than or equal to 0. So that's why we're just considering the first quadrant. So the first step that we need to do is we would determine the intercepts. So when we do that, we basically, well, we just need to set x cubed equal to 4x, and then we easily see that x is equal to 2, and of course 0. So the intercepts is basically 2 and 0. And then now we need to specify the integration path. So this would be the integration path. And we see that we go from x is equal to 0 to x is equal to 2, and then back to x is equal to 0. So now we've done this, and the third step is to find the area underneath the curve. And that area is given by minus the area inside the bounded curve of y dx. So this is equal to minus, firstly, the integral of the bottom curve from 0 to 2. The bottom curve corresponds to y cubed. Sorry, x cubed. Then back from a to 0. So we're going from 2 to 0, and that corresponds to the function 4x. So if we integrate this, the integral of x cubed is x to the power 4, and we have to put a 1 over 4 in front of it to cancel out the 4. And we're integrating this between 0 and 2. And 4x, if we integrate that, we get x squared. Then 2 times something must give us 4, and that's 2. And that we're integrating that from 2 to 0. So this is something that's not difficult to compute. 2 to the power 4 is 16. 16 divided by 4 is 4. Sorry, don't forget to put the minus in front. So we have minus 4, and then we have 2 squared. 2 squared again is 4, and remember it's minus now. So it's we put in 0, so this term, the first term is 0, so the second term is minus. So it's going to be minus 2 squared is 4. 4 times 2 is 8. So 4 minus 8 is minus 4. Minus 4 times minus 1 in front is just 4. So this illustrates the procedure of how to integrate inside a closed curve. And in a nutshell, all that we're doing is we're applying the integration along a certain path. We go along the bottom curve, then we go along the top curve, and we integrate just between these two paths. And the method or the formula requires consideration of both these curves, identifying the integration path as I've indicated, and then substituting all of this into our equation. That enables us to find the area inside a closed curve. In this video, we're going to be talking about line integrals. The next few videos are going to focus entirely on integration in terms of multivariable calculus. Line integrals do form part of that, and they're also going to come in when we look at vector calculus. However, this serves as an introduction to what it actually is. And what it actually is simply a function that's being integrated along a curve. Perhaps the easiest way to conceptualize line integrals would be to think about work done. If we have an object that's on the floor and we push it, in other words, we apply some force, perhaps that force is Ft, and then it moves a certain distance, delta S, then we would know from physics that the work done, W, is Ft delta S. So the work done is, of course, the energy required to move this object, this block, this distance delta S. So a line integral sort of follows that same thinking and that same methodology. It's a function that's acting across a certain distance. However, we would think about it in terms of a curve rather than a distance. So we can take that same example and we would look at it specifically in terms of a curve. Perhaps we could think of a roller coaster. And a roller coaster, of course, has a certain path that it follows, a trajectory. And it would start at the top of this incline, and then it would, of course, move downward. if we just take a snapshot when it's at the center, and if we just look at what's happening, what are the forces acting on the roller coaster? Well, it's the force of gravity. Call it Fg. So this gravity has two components. The one component is the tangent force. So we would think about the tangent as acting in that direction, and we would also think of a normal force, and that normal force is acting perpendicular to the surface of the track that the roller coaster is on. We'll call that Fn, and Ft is the tangential force. So we want to calculate the work done. How would we do that? What is the work done? We saw just now that the work done is just the force multiplied by the distance, right? So if we just think of a small distance, so that small distance is the length of this curve or this arc length, and we can call that delta S. So the work done is just going to be the force in the direction of delta S multiplied by delta S. So the work done would be Ft times delta S. So if we wanted to calculate the work done traveling from the top of this roller coaster to the bottom, maybe from point A to point B, then what we would have to do is we would have to add up all the chunks of delta S from A to B. So perhaps the work done, or let's call it I, the line integral. So the line integral from A to B, well, not the line integral at this stage, we're just calling it work done. But anyway, it's the sum of all these little chunks of delta S added up from A to B. So it's the sum of this tangent force. And of course, each point will have its own tangent. So there'd be a tangent there at that point, maybe another tangent like that. And we would have to add up the delta S's associated with each one of those tangents. So of course, we would also remember from single variable calculus that if we let delta S become infinitely small, then delta S becomes ds, an infinitesimal quantity. And then if we sum up the infinitesimal quantity between 2 points, then that summation becomes an integral. So we're integrating along the curve AB of this function ft, which we're thinking of as the work done in this context, multiplied by ds. So this is the line integral. So this, when we speak about a line integral, we're talking about this integral of some function along a certain curve or along a certain distance between 2 points AB. So this is our definition of an integral. So we need to take this just a little bit further. Sometimes it's not very practical to be integrating something along ds. And of course, there are ways to get around this, and perhaps we would look at something like that in later videos. But if we were to just break apart this red component, force component, and we just write it like that, and we can see that the work done is Ft, that's a T, delta S. So what we're going to do is break this up into two parts. So instead of this quantity, Ft delta S, we can think of two other quantities that we are now defining. We'll call it Q delta Y and P delta X. So we are creating these two quantities, P and Q, such that Ft delta S is equal to the sum of these two quantities. So we have chosen P and Q specifically so that it's equal to this Ft delta S. So Ft delta S is equal to P delta X plus Q delta Y. And of course, if we make delta X and delta Y infinitely small, as we have done with delta S, then we can just substitute this into our line integral. So that would mean that I now becomes the integral of, or rather between AB of P dx plus Q dy. So you might be thinking to yourself at this stage, okay, I've seen this thing before, PDX and QDY. In fact, I've seen it quite a lot if you've been looking at the previous videos. And you can see that we expressed function differentials in the form dz is equal to PDX plus QDY. So does this have anything to do with line integrals? The answer to that is yes, it does, but we're not going to go there just yet. There are a few other things we want to speak about and consider before we actually consider line integrals and differentials and exact differentials and what they all mean. So before we proceed any further, I think the next best thing would be to look at a simple example of how we actually calculate a line integral. So we have a certain curve, and that curve is y is equal to x, or rather 4x to the power 2, 4x squared. And this is defined with x and y greater than 0. And we have 2 points, O and B. And the curve between these 2 points is 4x squared. So it looks something like this. It's a quadratic. And where b is equal to 1, then y is equal to 4. So we want to do a line integral between O to B of a certain function. And that function is the integral of x squared plus 2y dx plus xy dy. So this is, of course, our P, and this is our Q. We don't really need to do anything with it being Q and P and Q at this stage. We just need to evaluate this integral. So between these 2 points, the curve is y is equal to 4x. So that means that dy is equal to 8x dx. So we simply substitute dy inside our line integral and 4x squared where we have y. So then doing that, and of course our integration bound is x, since we are making x the subject of our integration. So we're integrating from 0 to 1. So that's x squared plus 2y, so y is 4x squared, so 2 times 4 is 8. So we have 8x squared dx plus, well, we have x is just x, and then we are multiplying this by y, which is 4x squared, and we have dy, and dy is 8x dx. So proceeding with this as we would generally do, we just simplify it a bit. So x times x squared times x, this is going to be x to the power 4, and 8 times 4 is 32. So we would have x squared plus 8x squared, that just gives us 9x squared. And we saw that this is 32 x to the power 4 dx. Then integrating this, x squared becomes x cubed. 3 times something must give us 9. And of course, 3 times 3 is 9. X to the power 4, so this becomes x to the power 5. Then 5 times something must give us 32, and that would give us 32 over 5. 5 times 32 over 5 gives us 32. And we're integrating from 0 to 1. So, of course, 0, nothing is going to happen here. So we substitute in 1, and then what we're left with is 3 plus 32 over 5. And this is just 47 over 5. So this is how we determine a line integral. It's just some function that we are integrating along a curve between 2 points. And the easiest way to think about a line integral, an example of that would be the work done. So in the upcoming videos, we're going to be looking at how we integrate around a closed curve, and then how we apply line integrals to closed curves, and then the relationship between exact differentials and line integrals. In this video, we're going to be talking about line integrals around a closed curve. If you refer to one of the previous videos, we looked at how to evaluate the integral of some region bounded between two curves. If we take, for example, 2 points A and B, and there are two curves linking these 2 points, one curve at the top and one curve at the bottom. The bottom one is g of x and the top one is f of x. And the two x coordinates of these points are x1 and x2. And what we wanted to do was determine the area between these two curves, or this area in the middle. We saw that this is equal to minus this integral, and we put a little circle inside the integral. And that circle actually represented that we're integrating firstly along the bottom curve between x1 to x2 like that, and then we integrate back from b to a along the top curve. So it's along an anti-clockwise direction that we're actually integrating in. And the area in question is given by y dx, and we saw that this is actually minus, firstly along the bottom curve, the integral from x1 to x2 of gx dx, then the integral from x2 back to x1 of f of x dx. So the question at this stage is, in the same way that we evaluated a area between the two curves, can we actually integrate a line integral? So instead of determining the area between the curve, can we integrate some function between these 2 points a and b? Can we somehow integrate a line integral from a to b and then back from b to a? So the answer to that question is yes. So let's just remind ourselves what a line integral is, which we saw in the last video. It's just literally some function that's integrated between 2 points. For example, O to A, and the line integral is simply some function. We could think of it as perhaps ft being integrated between O to A and along the length of the curve O to A. And this is also equal to the integral of p dx plus q dy. So what we would actually now need to do is apply this to the closed curve. There's our 2 points A and B. We want to integrate some function from A to B and then another function from B to A. So this is different. This is not the area between the curves that we're evaluating. It's the line integral along this entire curve. So one property of line integrals that's very important to take note of is that we can only evaluate the line integral between 2 points of a curve if it is a single valued function. So take, for example, an ordinary curve like that. If we draw a vertical line, we can see that it only cuts the curve once. So that's a single valued function. On the other hand, if we have something like an ellipse, and if we draw a horizontal line again, you can see that it's cutting the curve at 2 points. So this would not be a single valued function. So the question is, how do we get around that situation? Well, what we have to do is we have to split it into 2 parts. So we would have to evaluate a line integral from A to B, and then again evaluate the line integral from B to A. So if we have a line integral and we simply evaluating it y dx, so maybe this y dx just corresponds to p dx, where the function, instead of some other long function p is just equal to y. So this would have to be firstly the integral, the line integral from a to b of y dx. then the line integral from b to a of y dx. So in a general form, we would just substitute p dx plus q dy. So this is from a to b. And then the integral from b to a of the same thing, p dx plus q dy. So I think that this concept is best illustrated through an example. Let's say we have a function that we're integrating. In same example, p dx, instead of p dx, we'll just have y dx. So we want to take the line integral of y dx along a certain curve. So this curve is actually a circle. It's a circle of radius 2. Okay, that does not look as if it has a radius 2. But anyway, I think we get the idea. So that's 2, minus 2, 2, and minus 2. So with the circle, we have two halves of the circle. And you can see that this is, of course, not a single valued function. So what we'd have to do is integrate two parts of the circle. We'd have to integrate perhaps the top half, and then we have to integrate the bottom half. We know that the formula for a circle, or the equation of a circle, is given as x squared plus y squared. In this case specifically, it's equal to 4, since the radius is 2. This 4 is r squared, and r is equal to 2. So the top half of the circle would correspond to the y values associated with that part of the equation, and of course the same is true of the bottom as well. So we'll have to solve for the equation of the circle and just express it in terms of y. And when we do that, we have y is equal to 4 minus x squared and the square root of that. So the top half of the circle is the square root of 4 minus x squared. Sorry, perhaps I should just write plus minus here. And the bottom half of the circle is minus the square root of 4 minus x squared. So now we can evaluate our line integral because we have y. Y is just plus minus 4 minus x squared. So we substitute that in and then proceed with the integration. Firstly, we have to break it into two halves, from 2 to minus 2, and then from minus 2 back to 2 again. So let's just draw the arrows. So we're integrating in that direction first, top half, and then the bottom half. So let's do this. So the top half, we're going from 2 to minus 2 of the function y. And the top half is given as square root of 4 minus x squared. That's 4 minus x squared dx. So this is what we're doing, evaluating the line integral. And then we're going from minus 2 to 2 of minus 4 minus x squared dx. So the first thing that we're going to do is try to simplify this integral to make it a bit easier to integrate. And of course, we know that it's easy to integrate if there's a zero involved, because it just means that there's less terms to evaluate. So that's what we're going to do. We're going to firstly swap this order of the integration. And when we do that, we of course need to change the sign. So this goes from a plus to a minus. So that's from minus 2 to 2 of 4 minus x squared. Okay, bring that minus to the front in the second term. This is also from minus 2 to 2, and that's 4 minus x squared as well. Let's not forget the dx. So you can see that the first term is the same as the second term. So it's just the same as 2 of the same integral. essentially minus 1 minus 1 gives us minus 2. So now we just split this up again just to make it a 0, so that we have a 0 in the integral. So that's minus 2 into, firstly, minus 2 to 0 of square root of 4 minus x squared dx, plus the integral from 0 to 2 of 4 minus x squared square root dx. So there's some symmetry involved here. So if you look at the circle, of course, integrating from 0 to minus 2 is the same thing as integrating from 0 to 2. So what we have on the one side, we should have on the other side as well. So what we're saying is that these terms of the integral are actually equal. So that term is actually equal to that term. So in the same way, we'll just add them together. Okay, so 1 plus 1 is 2, and then 2 times 2 is 4. So we'll have a minus 4 in front of the integral, and we'll have it from 0 to 2 of 4 minus x squared dx. So all we need to do at this stage is just evaluate this integral. The way to evaluate this integral would be to do a substitution, as is done in single variable calculus, and that is to let x equal to 2 sine theta. Then differentiating this, we get dx is equal to 2 cos theta. So if we just write down the term that's inside the integral, that is the square root of 4 minus x squared, then what this is, there's a dx as well. This is equal to the square root of 4 minus 4 sine squared theta, because of course the x squared, multiplied by dx, and dx is 2 cos theta d theta. So simplifying this, we just bring out 4 as a common factor inside the square root. So that gives us 4 into 1 minus sine squared theta times 2 cos theta d theta. We know from our laws of trigonometry, or rather our trigonometric identities, that sine squared theta plus cos squared theta is equal to 1. So I could just write that along the side. Sine squared theta plus cos squared theta is equal to 1. So cos squared theta is equal to 1 minus sine squared theta. So this part is simply cos squared theta. So we have the square root of 4 cos squared theta times 2 cos theta d theta. Square root of 4 is 2. Square root of cos squared is cos. So square root of 4, that's 2. 2 times 2 is 4. And cos theta times cos theta is cos squared theta. So there's just one more trig identity to remember, and that is cos 2 theta. So you'd remember that cos 2 theta is equal to 2 cos squared theta minus 1. So if we just solve for cos squared theta here, then we get that cos squared theta is equal to half 1 plus cos 2 theta. So we're just going to substitute that in as well. So the 4 times the half is just going to give us 2. So we have 2 into 1 plus cos 2 theta. d theta. So this is what our integral becomes. And of course, we're integrating a circle. And if we're integrating from 0 to 2, it means that we're integrating in the first quadrant. So the first quadrant simply corresponds to 0. So 0 to 2 just corresponds to 0 to 90 degrees, and 90 degrees is of course pi over 2 radians. So our integration bounds become 0 to pi over 2. So we're just going to substitute everything into our integral. So our integral now becomes this minus 4 multiplied by 2 gives us minus 8. So it's minus 8 times the integral from 0 to pi over 2 into 1 plus cos 2 theta d theta. Then integrating this, it becomes minus 8 into, well, the integral of 1 is just theta, and the integral of cos 2 theta is, well, the integral of cos is sine. But also remember that we have a function within a function, so we have 2 theta. So, sorry, I neglected to write the 2 theta here. So to cater for this 2 that's inside the sine, we have to put a half in front. And we're integrating from 0 to pi over 2. So when we do that, we get minus 8 into pi over 2 plus the integral of sine of 2 times pi over 2. So 2 times pi over 2 is just pi. Sine of pi is just 0. So this means that the final answer is simply minus 4 pi. So this whole long protracted example was just to show that we're integrating along a curve. This is the line integral along a curve. And when we do that, we have to split up our curve into 2 parts if it's not a single valued function, as was the case in this example. In this video, we're going to be looking at evaluating line integrals using arc length and parametric equations. We saw in previous videos that a line integral is some function integrated along some curve. And we saw that we can represent this as the sum of 2 different curves, or the sum of 2 different functions, p dx and q dy. The question at this stage is, instead of representing this integral on the left-hand side, ft ds, and evaluating it as 2 other different functions, can we just evaluate it directly? Well, we can do that if we represent ds in terms of the variables that can be integrated, specifically dx or dy. So basically what we do is we represent ds in terms of dx. Is there a way to do that? Well, it's covered quite extensively in single variable calculus, and the technique to do that is just to think about the theorem of Pythagoras. If you have a function and we have some length here, delta s, then we can just express that in terms of delta y and delta x. So by the theorem of Pythagoras, delta s squared is just delta x squared plus delta y squared. Then if we divide everything by delta x, then we get delta s divided by delta x squared equal to 1 plus delta y over delta x squared. So if we let delta x approach 0, then the deltas become d. Delta s, delta x becomes ds dx. So we get ds dx squared equal to 1 plus dy dx squared. So all we do is solve for ds. So that means that ds dx is equal to the square root of 1 plus dy dx squared. And of course, ds is just the previous term multiplied by dx. So if we substitute this into our line integral, what we're going to be left with is that I, which is initially equal to the function times ds, so this ds gets replaced by our integral, which is now in terms of dx. So it becomes ft multiplied by 1 plus dy dx squared times dx. We can illustrate this through a simple example. We can have some function that we want to evaluate the line integral for, and that could be between 2 points O and A, and the function that we're evaluating is 4x plus 3xy times ds. So this 4x plus 3y is our function. So we are evaluating this line integral between 2 points, and those 2 points are the origin and some other point A, where A is the coordinates 1, 2. And joining OA is a straight line. So what this tells us is that this curve is actually the line y is equal to 2x. So y is just double the value of x. The intercept is the point of origin, and it's a straight line, so yeah, y is equal to 2x. So that means that dy dx is equal to 2, and of course if we square this, dy dx squared, then we just get 4. So we want square root of 1 plus dy dx squared. So if we do that, so 1 plus dy dx squared is simply equal to 1 plus 4, which is equal to 5. So our initial integral required 4x plus 3xy. So if we take that down, what we're going to be left with is that I is equal to the integral from 0 to 1. That's our integration boundaries. And this function 4x plus 3xy. So y is equal to 2x. So we have to substitute that in. So x times x is x squared, and 3 times 2 is 6. So 3xy just becomes 3 times x times 2x, which is equal to 6x squared. Sorry. So that's equal to 6x squared. So if we put that into our integral, that becomes 6x squared. And also, we cannot forget that we have to put in our ds, and our ds is equal to the square root of this. Sorry, I kind of just let it get all a bit muddled here. Yeah, so I will just bring it below. Yeah, so that's our function, and we have to have the square root of 1 plus dy dx squared, and that's the square root of 5. And of course multiplied by dx. So we have our function, and we have ds. So it's just a simple matter to evaluate this integral. So this root 5, that's just a constant. We can bring it to the front. The integral of x is x squared, and we need to multiply it by something to get 4, and that's going to be 2. integral of x squared is x cubed, so 3 times something needs to give us 6, and that number would be 2. And we're integrating this between 0 and 1. So the integral of just substituting 1 in, it's just going to give us just the number in front of the x. So 2 plus 2 is 4. So 4 times root 5 is just 4 root 5. Okay, so that's how we would do an example in which we substituted ds using arc length, the equation for arc length, that is, and it enabled us to find the integral directly without having to substitute p dx plus q dy. So we can also evaluate the line integral directly if we look at parametric equations. So let's just write our line integral again. So it's the integral along some curve of some function acting along a certain arc of a curve. And instead of integrating with x as we had done using arc length, we can now perhaps use another variable, for example, t, dt. Well, it could be anything. So once again, we could look at the theorem of Pythagoras. Delta s squared is equal to delta x squared plus delta y squared. And all we'll do is simply just divide by the variable that we want to now look at it in terms of, in this case, t. We'll divide this entire equation by delta t, of course, squared. Delta t squared. So we just solve for ds as we had done previously, but before that we let delta t approach 0. So delta s delta t becomes ds dt. So if we do that, we solve for ds, what we get is that ds is equal to the square root of dx dt squared plus dy dt squared multiplied by dx. So our line integral now becomes substituted in for ds. So that would be the function times ds, and ds is everything that I've just underlined. So it's the square root of dx dt squared plus dy dt squared times dt. So we can illustrate this through a simple numeric example, and that would be to integrate the line integral. I is equal to the integral of some curve of the function 4xy ds, and we would need some equations. We would need x to be in terms of t and also y to be some equation of t. So we could say that x is equal to sine t and y is equal to cos t. These are just parametric equations. We have x and y in terms of the other variable t. So we're expressing ds in terms of t. So to use our equation that we have derived, we would need to find dx dt, dy dt, square both of them, take the square root, substitute it into this integral, and then evaluate the integral. Perhaps we should also mention that this curve requires t to go from 0 to pi over 4. So this is our integration boundaries. We would need to find dx dt. So dx dt is, let me just write it like this. Dx dt is equal to cos of t, derivative of sine is cos. Similarly, the derivative of y, so dy dt, is equal to minus sine t. Derivative of cos is minus sine. So we need to square dx dt and dy dt. And when we do that, we get dx dt squared simply equal to cos squared t, and dy dt squared equal to sine squared t. And of course, the equation requires us to add both of them and take the square root of it. So cos squared t plus sine squared t is simply going to give us 1 through the trigonometric identity. And if we do that, Okay, let's just write it first. So dx dt squared plus dy dt squared is equal to cos squared t plus sine squared t, which is equal to 1. So what that means is that ds is equal to dt. What is ds equal to? We can see from our equation that ds is equal to the square root of dx dt squared plus dy dt squared times, sorry, this should be dt. Well, we have just shown that this dx dt squared plus dy dt squared is equal to 1. And of course, the square root of 1 is just 1. So that means that ds is equal to dt. So all that's required for us now to do is just to substitute everything into our line integral, which we will now do. And if we do that, we see that I, our line integral, is equal to, firstly, our integration boundaries is from 0 to pi over 4, which has been defined as part of the example that we're solving. And 4 times xy. 4 times xy is just 4 times sine t x times cos t, which is y. And of course, ds we saw was equal to dt, so we just substitute in dt. If we look at this term inside the integral, we see that it actually very similar, it very closely matches our trig identity. And that identity that we're talking about is that sine of 2a is equal to 2 sine a cos a. So we would now put that into our integral. So what this means is that I now becomes 2 times the integral from 0 to pi over 4 of 2 sine 2 theta. Sorry, there should not be a 2 there in front. We've already put it in front of the integral. It becomes sine of 2t dt. So all that's left is to evaluate the integral. The integral of sine is minus cos. So we'll have a minus cos 2t. And since we have a function inside a function, we have to somehow cater for this 2t, and the integral of this 2t is half. If you differentiate this, the derivative of cos is sine, and the derivative of this 2t is just 2, and this 2 times the half gives us 1. So that caters for the 1 in front of the sine. So 2 times pi over 2 is, 2 times pi over 4 is pi over 2, and cos of pi over 2 is simply equal to 1. Sorry, my apologies. Cos of pi over 2 is equal to 0. So this first term basically disappears from the integral, and then we have cos of 0. Cos of 0 is 1. So minus half times 1 is minus half, and there's already, maybe we should just expand it out. So we have 0 minus minus a half, and this will leave us with 1. So the whole purpose of this example was to illustrate how we can convert our line integral ds to be in terms of some other variable, and the example used was t. So the whole purpose of this video in general was to evaluate the line integral to be in terms of other variables such as dx and dt, such that we don't have to use some other form of the integral, for example, pdx plus qdy. In this video, we're going to be looking at the path dependence of line integrals. We've seen that the general form of a line integral is equal to the integral of some curve between 2 points of some function multiplied by ds, and we saw that this can be expressed as the integral of p dx plus q dy. In the first time this was mentioned in one of the previous videos, we said that this p dx q dy kind of looks like the differential, the function differential, where we said dz is equal to p dx plus q dy. And the question we asked at the time was, does this have anything to do with line integrals? It kind of looks, it has the same form, right? So the answer to that question is yes, we can think of the line integral as being an exact differential. So let's just remind ourselves what an exact differential is. If we have some function z being the function of x and y, and then we find the differential of z, and then we see that it's dz dx times dx plus dz dy dy, and we said that p was equal to dz dx and q was equal to dz dy. And we said that if z or dz is an exact differential, then if we differentiate this first derivative with respect to y, it should equal to this other derivative with respect to x, because we know that mixed partials are equal. That is, d squared z with respect to x and then with respect to y should equal to the same thing, but initially with respect to y and after that with respect to x. So if this is true, then our function is an exact differential. So what this means is that the derivative of p with respect to y should equal to the derivative of q with respect to x, mixed partials. So what does this have to do with line integrals? So what it has to do with line integrals is that when we take an integral over a closed boundary, remember when we put the circle in this integral sign, it means it's a closed boundary. When we take the integral of around a closed boundary of an exact differential, the integral of an exact differential, we get 0. Literally, that is exactly what it means. So let's just rewrite this into a way that we understand it. So it means that if we integrate I around a closed boundary of a curve of p dx plus q dy, and p dx plus q dy is an exact differential, then we should get 0. So I think this point is most easily illustrated through an example. So let's just take some function differential. We say 3x squared, perhaps y squared dx. So this is our p, plus 2x cubed y dy, and this is our q. So if this is an exact differential, it means that the derivative of p with respect to y should equal to the derivative of q with respect to x. So let's do that. So p is equal to 3x squared y squared. If we differentiate this with respect to y, then we find that it's equal to just 6x squared y. So if we do the same with q, and then differentiate it with respect to x, that's dq dx. Well, 2 times 2 is 4. Sorry, this is a cubed. Yeah, it's a cubed. Okay, so 3 times 2 is 6, and 3 minus 2 is 2. We get 6x squared y. So what do we see? We see that indeed the derivative of p with respect to y is equal to the derivative of q with respect to x. So this means that it is an exact differential. So if we were to integrate this, if this is our function, and if we integrate it around any closed curve, we should get 0. This is what our assertion is. So that's what we're going to do. We're going to integrate this function, 3x squared, y squared, 2x cubed, y, and let's see if it does in fact give us 0. So we'll take the curve, let's just draw a curve. We'll take two curves. One will be a quadratic curve between 2 points, and one will be a straight line between the same points. So let's, as the curve, we'll choose it to be y is equal to 2x squared. Okay, so let the point be something like a. Okay, then also be the top curve, let it be, for example, 2x. So it's a closed curve that we are evaluating. So our line integral was around the closed curve of this exact differential, and it was 3x squared y squared dx plus 2x cubed y dy. Right, so let's firstly do the two curves. So we have y is equal to 2x squared, that's our bottom curve. So that means that dy here is equal to 4x. And of course, y is equal to 2x, that is our top curve. So dy is equal to 2 dx. So we substitute this into our line integral. So let's write the line integral for both curves. Remember that this is not a single valued function. And in the previous videos, you saw that we had to split it up into two parts. So we have to integrate the line integral from O to A and then from A to O. So let's do that. So the line integral would be from initially, well, A is the point, let's just say 0 to 1. And of course, the y value is 2. So we'll integrate from 0 to 1 along the bottom curve. So that would be 3x squared times y squared, and y squared is 2x squared. So that's 2x squared times dx plus 2x cubed times y dy. Y is 2x squared and dy is 4x. So we have to multiply it by 2x squared and dy, which is 4x dx. And let's not forget that we have to add this to this now. The integral from 1 to 0. Same thing, but now y is equal to 2x. So again, it will be 3x squared times y squared. So it'll be 2x this time, squared, times dx, plus 2x cubed times y, which is 2x, multiplied by dy, which is 2 dx. Simplifying this, 3x squared times 2x squared squared. So x squared squared is x to the power 4. X to the power 4 times x squared is x to the power 6. And 3 times 2 squared, well, 2 squared is 4. 4 times 3 is 12. So we're going to have 12x to the power 6. That's this first term. Let's look at the second term. We have x cubed times x squared. That's x to the power 5 times another x. This is that'll make it x to the power 6. So we have 2x to the power 6's, so we can add them up. So this is the first term was 12x to the power 6, and the second one is 2 times 2 is 4. 4 times 4 is 16. So we have 16x to the power 6 dx. So that's our first integral. And then we add now to this our second integral, second term. So that's from 1 to 0. X squared times x squared is x to the power 4. 2 squared is 4. 4 times 3 is again 12. So we have 12 x to the power 4. And then let's look at the second term. We have x cubed times x, that's x to the power 4. 2 times 2 is 4. 4 times 2 is 8. So we have x to the power 4 as well. So we can just add to this. So that will give us 8x to the power 4 dx. We can just simplify this. So 12 plus 16 is 28. So we have 28x to the power 6 dx. So what we can do is, instead of integrating from 1 to 0, we can just reverse the order of integration. And of course, we have to change the sign when we do that. And 12 plus 8 is 20. So we have 20x to the power 4 dx. So just remember that this first integral corresponds to our bottom curve, that was y is equal to x to the power, y is equal to 2x squared. And the second term corresponds to the top curve, which was y is equal to 2x. Let's just remind ourselves. So that's 2x squared. And that was 2x. So that was the first term, and this is the second term. So if we now integrate these terms, what do we get? X to the power 6, that becomes x to the power 7. 7 times what gives us 28? Well, that's 4. Doing the same with the other term, x to the power 4 becomes x to the power 5. 5 times 4 gives us 20. So evaluating this integral, anything to the power 1 to the power anything is just 1. So we have 4 as the first term and 4 as the second term. What does this give us? 4 minus 4 is 0. So yes, if we integrate this exact differential around this closed curve, it gives us 0, as we had asserted earlier on in this video. So that illustrates the point that if we have an exact differential, and we prove that it's an exact differential by finding day p, day y, and showing that it's equal to day q, day x, and then integrating it, if it's a closed boundary, it will always give 0. So that's the one point. The other point is that if we integrate along this closed boundary, it means that no matter what path I take to get from O to A, I will always get the same value. So let's just explain that once again. It means that if I integrate, I could integrate like that. That's one path I could take. I could integrate maybe another path from here to here. I could also maybe integrate from there to there. There's an infinite number of ways I can get between these 2 points, O and A. Perhaps another path could be the straight line, as we've looked at earlier in this thing. Sorry, let me just use another color there. So regardless of the path that we take from O to A, we'll get the exact same value, because if we go back along any other path, we'll get the same value, because the integral of the exact differential should be 0. So let's prove that point. I think it'll become evident what I mean if we just look at this example that we have just done. So let's just say we looked at it in reverse. So instead of integrating from O to A and then back along this other curve, the top curve that is, let's just say we integrated from O to A, and then we also integrated from O to A as two separate line integrals. So let's just say I1 is along the path O to A of this function. And let's just say I2 is the integral also from O to A of this other function along y is equal, OA is equal to 2x squared. It's not actually equal to, but we're just using it as an indicator to show what we mean. So let's look at this. We said that the integral along the one curve was 4, right? So this was equal to 4. So it's drawn as an arrow there. So that term corresponds to the integral I1. And we saw that it's equal to 4. And this corresponds to the integral I2. We're going along y is equal to 2x. And that's also equal to 4. So it means that regardless of how we get from O to A, we'll get the same value of the integral. So there's two important points that have come out from this video. And I just want to write those 2 points are, what those 2 points are. So number one, so if p dx plus q dy is an exact differential, then the line integral, so the line integral of the exact differential around a closed curve is equal to 0. So the line integral of an exact differential around a closed curve is equal to 0. That's the first important point of this video. So the second important point is that if this first point is true, then it means that the line integral, so the line integral between 2 points does not depend on the path of integration. The line integral between 2 points does not depend on the path of integration. The path of integration. Yeah. So we have already shown how one is true by using an example. We proved that the function that we're integrating was an exact differential by taking day p, day y, and day q, day x, and showing that it's equal. And once we proved it was an exact differential, we integrated along the two parts. One was 4x squared, was it 2x squared? Well, whatever it was, and along 2x, yeah, it was 2x squared. So we integrated along these two parts, and we showed that it's equal to 0. Then the second thing we did was we showed that the first part, the integral, gave us 4, and also along 2x it was also 4. That means it doesn't matter how we got from O to A, we still had the same value of the integral. So this is a very important point. So that means that for an exact differential, we use the phrase path independent. In this video, we're going to be looking at how to evaluate multiple integrals. If we think back to single variable calculus, we looked at how to calculate the area underneath the curve. we saw that if you have some kind of random curve and we wanted to compute the area underneath it, what we did that was we broke it into little strips. We could have a little strip like that. And the width of the strip would be the length delta x, and the height of the strip would be just the value y, as it is just the y value. And then we looked at taking this strip along the entire part of the curve which we wanted to determine the area underneath, and then we added all of them up. So adding all of them up, it's the sum of the area of one of these strips. So that's length is delta x times y. So if we now consider this in terms of a function, and then we consider these little strips as becoming infinitely small, then this delta x approaches dx as this delta x becomes very small. So this summation sign becomes replaced with an integral sign. So the area underneath the curve becomes the integral between the two parts of the curve, for example, x1 to x2, and summing up all of these different strips. So we just get y dx from x1 to x2. So the idea now is to extend this into more than one variable. So we'll start by looking at the area of just a shape, still in the Cartesian plane, and still 2 dimensions. So from a single integral, we're going to go to a double integral. We could have some kind of shape, and we look at a little, just a little square inside the shape, and the width is delta x and the height is delta y. So if we're now wanting to sum up this little square over our entire shape, we have to add it up in 2 dimensions. We're going to have to do it firstly across the x dimension, or along the x plane, carrying on like that, and then also extending this entire thing along the y-axis, and that will give us the entire shape of the area of the shape. So doing our summation, we're summing up all the little bits of delta x and delta y, and this is of course a double summation. So if we let delta x and delta y both to approach 0, then they become dx and dy, as was the case before. And instead of this summation sign sigma, we have 2 integrals going from x1 to x2 and y1 to y2. And of course, it's dx dy. So the way in which this type of integral is actually calculated is by looking at, firstly, one of the integrals, evaluating that, we'll call it the inside integral, and then evaluating the outside integral. So we do this part first, the inner, and then we do the outer. I think this is most easily illustrated with the use of a simple example. We would like to calculate or evaluate some kind of integral, which is a double integral, where there's 2 bounds for each integral. In this case, the outer integral is going from 1 to 2, and the inner integral is going from 2 to 4. And we are evaluating the integral of the function x plus 2y dx dy. So as I've just stated, the technique is to evaluate the inner integral first, and thereafter the outer integral. So if we're doing the inner integral with respect to dx, what it means is that we're treating y as a constant. So we're only integrating with respect to x while treating y as a constant. So we keep the outer integral as is, and now we integrate what's inside. So the integral of x with respect to x is a half x squared, and the integral of 2y, where 2y is being treated as a constant, and therefore that is 2xy. So just the derivative of x becomes 1, and then you're left with 2y. And then this is being integrated from 2 to 4. Since we have already integrated with x, we can remove that dx. So we will just write dy at the end. We now evaluate this integral as we've done in all previous cases. We would just substitute in 4 and then minus, then after substituting in 2. So doing that, we leave the outer integral as is for now, and then we substitute in 4. So 4 squared is 16, and 16 divided by 2 is 8. Then substituting in 4 here, we have 2 times 4 times y. 2 times 4 is 8, so we're left with 8y. So now we subtract, and then we substitute in the lower bound. 2 squared is 4, 4 divided by 2 is 2, and then 2 times 2 is 4. That would be 4y. And we leave the dy as is for now. And then we simplify it. So 8 minus 2 is 6. And 8y minus 4y is 4y. So we now integrate this with respect to y. So that gives us 6y, the first term, and then y squared. So what times y squared gives us 2 times what gives us 4, and that's 2. So the integral of 4y is 2y squared, and we're integrating this from 1 to 2. Substituting it in as we would usually do. 6 times 2 is 12, and then 2 squared is 4. 4 times 2 is 8. Then we have minus, we just substitute in 1, so we have minus 6, minus 2. So 12 plus 8 is 20, 20 minus 6 is 14, 14 minus 2 is 12. So this is a simple example of how we would integrate a double integral. So the technique is just simply to do the inner integral first, thereafter the outer, and when we're doing the inner integral, we would simply keep the other variable constant. So we're now looking at triple integrals. We would need to draw our figure in 3 space to be able to show this. So a triple integral of a function would typically give you the volume of that specific function within a particular region. So we could have a 3-dimensional cube, for example. So we would have 3 axes, that would be the x, y, and z axis, and we would have our shape, the 3D shape. And within this 3D shape, we can isolate just a little section, and we could have a 3-dimensional block, a volume block, as we would want to think about it. There's our little volume block, just as we had a little volume area. This is now a volume block that we will be integrating. So that's delta y. This is delta x. Sorry, my apologies. That's delta y, that's delta x, and the height is delta z. So we sum up this little block in 3 dimensions. It would have to go up, it would have to go along the x-axis, and along the y-axis as well. That's the y-axis. So if we wanted to compute the volume, we would have 3 summations of delta x, delta y, and delta z. And then, of course, if we let delta x, delta y, and delta z approach 0, and it becomes dx, dy, and dz, then we have the triple integral of dx, dy, and dz. And then this is computed over some region. So the way in which we would solve this, or we would calculate it, is by doing it the same way we had done the double integral. So instead of one inner integral, we have two inner integrals. We would do the integral with respect to dx, then with respect to dy, and then lastly we would complete it by integrating with respect to dz. So we can illustrate that with a simple example, and that example is to do the integral evaluated of, we have three integrals, three bounds. So integrating from -3 to 3, from 1 to 3, then -1 to +1, and then from 0 to 2. And we're integrating the function x plus 2y minus z. So we would do it with respect to x first, and that means leaving the rest of the terms as is, the rest of the integrals. So we would keep it from 1 to 3, -1 to 1, and then integrating with respect to x, we have a half x squared plus 2xy minus xz. And this is from 0 to 2. And since we have now integrated with respect to x, we just left with dy and dz. So if we substitute in 2 and 0, what we're left with is still the same integrals as they were. And substituting in 2, we have 2 squared divided by 2, and that gives us 2. And then we have 2 times 2, so we have plus 4y. And minus 2 times z. And of course, substituting in 0 leaves us with no terms, as each one has x in it. So then we integrate with respect to dy and dz. So now we do the next inner integral. So that's the inner integral from 1 to 3. Then integrating with respect to y, we get 2y plus y squared, 2y squared, 2 times 2 gives us 4, minus 2yz, integrated from 1 to -1. So now we substitute in these two bounds. So the outer integral remains the same. We now substitute in 1. So 2 times 1 is just 2. 1 squared times 2 is also 2. And substituting in 1, we left with minus 2z. Now we minus 1 times 2 gives us minus 2. Minus 1 squared is 1. So we still have plus 2. And minus times minus gives us plus. So we have plus 2z. And all of this is still going to be integrated with respect to z. Simplifying this, 2 plus 2 is 4, minus 2z, and minus 2 and plus 2 are going to cancel out. So we have minus 2z, so we're left with minus 4z. So now we integrate this. The integral of 4 is just 4z. We have z squared. So that gives us 2z squared, and integrated from 1 to 3. So it's just a simple matter to compute this. 4 times 3 is 12. 3 squared is 9. 9 times 2 is 18, so you have minus 18. And then with the 1, 4 times 1 is 4. 1 squared times minus 2 is minus 2. 12 minus 18 is minus 6. Minus 6 minus 4 is minus 10. Minus 10 plus 2 is minus 8. So this is a simple illustration of how we would integrate multiple integrals, that is double integrals and triple integrals. So just one final point before this video concludes is that we can reverse the order of integration. If we have a double integral that's going from y1 to y2 and the inner integral from x1 to x2, dx, dy, we can actually reverse this order of integration. So what this means is that the outer becomes the inner and the inner becomes the outer. So this can also be rewritten as the integral with x being the outer integral. So it's going from x1 to x2 and y going from y1 to y2, dy dx. So we would integrate with respect to y first and thereafter integrate with x. So in both instances, we would get the same answer. In this video, we're going to be looking at an application of double integrals or an application of multiple integrals in general. And this specific application that we're looking at is finding the center of mass of some given object or region in space or something like that. So we're going to look at an example firstly, and that is the plane figure of some kind of triangular plate. So we have our Cartesian axis like this, and this triangular plate looks something like this. So this curve is y is equal to 2x, and this point is 2, 0. And the point where these two lines intersect is 2, 4. X coordinate of 2 and y coordinate of 4. So we have this region here and we want to find the center of mass or the center of gravity of it. And what's important in this example is to note that the density of this object is variable. So we are told that the density is governed by the function 1 plus x plus xy. So what do we mean when we say variable density? It means that the mass of this object depends on its position, where this particular part of this object you're looking at. For example, if you think of a hammer with a metal head, a steel head, and a wooden handle. So we can see that the mass of the hammer is more concentrated at the head of the hammer. So in the same instance here, we can see that the density depends on the x and the y coordinates. So we can understand that it's more heavier, that this object is more heavier in this region here. So how do we find the center of mass? So what do we understand by center of mass to begin with? So if we think about a seesaw, for example, or some kind of object where we want to understand how to position something. So we can perhaps think of a number line here, where this x position is 0 and at some general point, and we have two objects on this seesaw, some mass, maybe m1, and maybe some other bigger mass, m2. So this m1 is at position x1 and this m2 is at position x2. So the question is, where would we need to put some kind of pivot or something like that to make sure that this structure is completely balanced? Should we put it here, or should we put it maybe here, or maybe even something here? Our intuition would tell us that, or experience will tell us that perhaps we should position it somewhere here. And leaving our intuition aside, how can we know this in terms of the mathematics? Well, we can understand that it's more heavier on this right-hand side. And what we're seeing is that it should be closer to the heavier object. So this is what our experience tells us. So we can just maybe assume that that pivot point or that center of mass is located here, and it has the coordinates x bar. So how do we know what the specific position is? Okay, so we've identified two variables that it does depend on. It depends on the position away from this center point, and also it depends on the mass of the objects that are involved. So let's say that the distance from x1 to x bar is d1, and the position from x bar to x2 is d2. So what this means is that if we take the product of m1 and d1, it should equal to the product of m2 d2. So this is actually something called Archimedes' principle, or the lever rule. So if we substitute that in, we see that m1 is multiplied by x bar minus x1. So that's what d1 is. d1 is x bar minus x1. And then this is equal to m2. So now we can see that x2 is on the right-hand side of x bar. So what this means is that it's actually x2 minus x bar. So if we do some just mathematical manipulation here, collecting all the terms, we see that we get m1 into x bar minus m1 times x1, and then this is equal to m2 times x2 minus m2 x bar. And then collecting all the terms, we get x bar into m1 plus m2 being equal to m1 x1 plus m2 x2. m2 x2. So if we now solve for x bar, what we get is x bar is equal to m1 x1 plus m2 x2 divided by m1 plus m2. So if we were to analyze this expression that we have, we're saying that the center of gravity, or the center of mass, is simply equal to the sum of the products of the masses and the positions divided by the total mass of the object. So this quantity in the numerator, this product of mass and position, so that is given the name, the moment. It's called the first moment. And in order to find the center of gravity or center of mass of any kind of object, we need to take its moment, as it's called. So there's two quantities that we need to determine. It is the moment and of course the total mass. So this is true of the x coordinate. So if we were to take some kind of plane figure, not just one-dimensional as what I have drawn here, if we were to take a two-dimensional shape, then we can see that there will be an x coordinate and a y coordinate. So the x coordinate remains the same, and the y coordinate is simply taking the moment as well, but here we would multiply by the y position. So now we can go back to the example that we were looking at. We have some kind of plane figure, a triangular plate, and the x position is 0 and 2, and the y position of this point, two-dimensional point, is, or the boundary of it is 2, 4. So we can see that we have the density now equal to 1 plus x plus xy. We saw that from the derivation that we've just done, we need to find the total mass. So in order to find the total mass, we need to actually consider this variable density. And how do we do that? We know as a general understanding of density as being mass divided by volume. But since this is a very thin plate, its height is negligible, then we can think of it as being the mass divided by the area.
So it's the area density. So the total mass then is equal to the density multiplied by the total area. And how would we determine the area of a figure like this? Well, we can use a double integral. We can just take a thin strip and we can identify a little block of it and then integrate across the various boundaries. So what we're saying is that the area is actually double integral of dx dy. And let's look at the boundaries. So we're integrating x from 0 to 2. However, we're integrating y from 0 to 2x. Remember that this line is given by the function y is equal to 2x. So we have to integrate y from 0 to 2x. So we can't have the outer integral as integrating to a variable. So what we should do is reverse this order of integration. So what this means is that we now integrate x from 0 to 2 as the outer integral, and the inner integral being from 0 to 2x dy dx. So we just swapped the dx and dy around, and therefore we have swapped the order of integration. So we can integrate y with respect to 2x, and that leaves us only with x as the variable to integrate with, and then we can just integrate x from 0 to 2. However, remember what we're actually trying to do is determine the total mass, and the total mass is actually the density multiplied by the area. So we now write this area integral, but we have to multiply by the density as well. So we're going to substitute this row for 1 plus x plus xy. So that's 1 plus x plus xy dy dx. And all we need to do is now simply just integrate this. So integrating that, firstly with respect to y, what we would get is, firstly, we just write the outer integral as is, and what we're left with is y plus xy plus a half xy squared. And this is integrated from 0 to 2x. When we substitute in our boundaries, it's going from 0 to 2x. So we just substitute in 2x in the first term, then we'll have x multiplied by 2x here, and of course now we'll have 2x squared in the last term. So we're left with 2x, and 2x times x is just 2x squared, plus, firstly, 2 squared is 4, 4 divided by 2 is 2, and x times x squared is just x cubed, so we're left with 2x cubed. And now we simply just integrate this with respect to dx, and that's simply a fairly simple matter to do at this stage. All we're left with is x squared plus 2 over 3 x cubed plus 1 over 2 x to the power 4. Sorry, this integration boundary is 2. So all we do is we substitute in 2, and when we do that, we get 4 plus 16 over 3. This 2 cubed is 8, 8 times 2 is 16, and that's how we get 16 over 3, plus 8. 2 to the power 4 is 16, 16 divided by 2 is 8, and that, if we just add it up, we see that we get 52 over 3. So this is what the total mass is equal to. So the total mass is equal to 52 over 3. So this is just the first step that we need to take to find the center of mass. So this is just the denominator of the center of mass equation. We can see that the center of mass, as we had derived it earlier, is equal to, or the x coordinate is simply equal to the mass, or rather the sum of the masses multiplied by the x coordinate, which you know now is called the moment, and divided by the total mass, in this case m. So we've determined this mass, and we now need to do the moments. So it's the mass multiplied by the position. So we'll take the moments. So the moments, we can see that all we do is we have the density multiplied by the area, which is of course our double integral. So we still have our double integral the same as is. So it's 0 to 2x, and our y is being integrated from 0 to 2. So instead of the density, we'll write our function, which we know what the density is equal to, 1 plus xy. And now we have to multiply by the x position. So we're multiplying by x. And of course, dy dx. And we have to divide that by the total mass. And we saw that this is 52 over 3, but we don't need to substitute in at this stage. We'll evaluate the integral first. And after we expand this integral, we just multiply everything by x. We're left with our outer integral and inner integral remaining the same. And then we have x plus x squared plus x squared y. dy dx divided by the total mass. So we integrate it with respect to y first, as we've done it just now with the mass, and then we continue with the problem as was done just now. So integrating with respect to y first, we leave our outer integral the same for now, and then integrating with respect to y, we have xy plus x squared y plus a half x squared y squared. Okay, so my apologies, that should be from 0 to 2, and we're integrating here from 0 to 2x. And we're dividing by m. So substituting 2x into this, what we're left with is 2x squared plus 2x cubed plus 2x to the power 4. If we substitute in 2x, 2 squared gives us 4, 4 divided by 2 is 2, and then x squared times x squared is x to the power 4. And now all we're doing is just integrating this with respect to x. And if we continue with that, what we're left with is 2 over 3 x cubed plus a half x to the power 4 plus 2 over 5 x to the power 5, and integrating this from 0 to 2. So if we do all these substitutions, then we get 16 over 3 plus 8 plus 64 over 5. And this is all divided by the mass, and the mass we saw was, sorry, that's divided by 52 over 3. And if we just substitute all of this in and do this computation, we see that we get something like 98 divided by 65. So this is roughly something like 1.5. 1.51 or something like that. So this was the x coordinate. So the y coordinate is fairly straightforward. It's the same thing. To get the y coordinate of the center of gravity, all we do is we repeat the same integral, 0 to 2, 0 to 2x, and all that happens is now we multiply by y. Y is the position that we're multiplying by. So it'll be y times the density, and so it's y into 1 plus x plus xy dy dx, and we, of course, we're dividing by the mass. So expanding out this integral, or the term inside the integral, it still remains the same. That is the boundaries, 0 to 2, 0 to 2x, then multiplying everything by y. We get y plus xy plus xy squared. That's dy dx divided by the mass. So proceeding with this integral as has been done previously, integrating with respect to y, we get a half y squared plus a half xy squared plus 1 over 3 xy cubed. And that's being integrated from 0 to 2x divided by the mass. So substituting in 2x, 2 squared is 4. 4 divided by 2 is 2, so we get 2 and then x squared. So again, we'll be left with 2 here, and then x squared times x is x cubed. And then x cubed times x is x to the power 4. 2 cubed is 8, so we have 8 over 3. And then dx divided by the mass. So integrating this, what we're left with is 2 over 3 x to the power x cubed plus half x to the power 4 plus 8 over 15 times x to the power 5. And this is integrated from 0 to 2 divided by the mass. So substituting in 2, what we get is 16 over 3. This is a 3. Plus 8 plus 256 over 15. And of course, this is divided by the mass, and the mass we can substitute it in now, which we determined earlier was 52 over 3. And if we compute this, we see that it's about 1.75, approximately. So our center of mass roughly has the position of 1.5 to about 1.75. In this video, we're going to be talking about cylindrical and spherical coordinates. In mathematics, people are always looking for easier way to do things. Integration is quite difficult at times, and we can end up with integrals that can be hard to evaluate. So what people do is that they change the coordinate system. Often when you change the variables to be in terms of one variable and change it to another coordinate system, we find that the integration becomes much easier. So cylindrical and spherical coordinates are two different coordinate systems. The variables are changed to be in terms of other variables, and what happens is that certain figures become much easier to evaluate, that is in terms of integration. So we can start off with cylindrical coordinates, and we would use cylindrical coordinates when there is an axis of symmetry. The integrals become much easier to evaluate when there is. When I mean axis of symmetry, I mean, for example, if you have a simple parabola, then we can see that the y-axis is actually an axis of symmetry. And in 3 space, we can think of the z-axis as being the axis of symmetry. And that's what we're going to look at now. So there is a change of variables that goes from x, y, z to that of r, theta, z. So from x and y, we transform it into r and theta. So this change of transformation, this change of variables is actually the same as the change of variables to polar coordinates, except that now we in 3 dimensions, and we're also including the variable z in the polar coordinate system. So if we have a cylinder, and that's what we're doing, we're converting to cylindrical coordinates. And if we just take a point on the cylinder, a random point that is, and we think about its projection on the xy plane, the height of this point, that is from the base to the point, is just z, so that doesn't change in this coordinate system. Z remains the same. What does change is the x and y. And what happens is we consider the r, as is the case with polar coordinates, to be the radius from the point of origin to the point on the cylinder. So that's what r is. And then we also include theta. So theta is just the distance from the x-axis to the point itself. So that's x, y, and z. So if we do our conversions, if we convert to the x and y coordinates, we can see that x is simply r cos theta, as was the case with polar coordinates. So we can understand this by just looking at the basic triangle. So there's our triangle, there's our angle theta, and this is x and y. So, and that's r. So of course cos theta is x over r. So x is r cos theta. So y is also done in similar manner. So y is r sine theta. Z just remains as z. There's no transformation of variables there. And r, by the theorem of Pythagoras, is just the square root of x squared plus y squared. And of course, theta is arctan of y over x. So this is the transformation of variables, and it's actually quite a simple matter to do this conversion. If we're given a point, any point, and if we want to convert it into cylindrical coordinates, all we just do is use these equations. So this is very nice and easy to do, but the whole point of converting something to cylindrical coordinates would be to make the integration easier. That is the whole purpose of why we are performing this exercise. So how do we actually now integrate using cylindrical coordinates? Well, as was the case in the normal coordinates with x, y, and z, all we do is we take a volume element. So we have a volume element, and of course it's just dy, dx, and dz, and then all we do is we integrate. It becomes a triple integral of dx, dy, and dz. So all we do is we do the same thing with cylindrical coordinates. We take a volume element and we multiply everything by this change in variables. So our volume element, if we can just draw it around the point, would be something like that. We would take the volume element and then we're going to integrate it around our various boundaries. So that has been just drawn here. So we can see that radius is, well, it's the same both in the segment and its projection in the xy plane. So that is the radius, and this is a differential change in the radius. So that's dr, and of course that's the same with projection, that's dr. And this angle theta, so this is a change in the angle theta, so that's just d theta, and it's the same here on the top. So that's d theta. And this other part of the curve, so that's r d theta. It's easy to understand this. If we have a circle and we take a segment of the circle, so that's the radius. So when this segment of the circle, or when the length of the circle equals the radius, then we define the angle to be 1 radian. So theta is equal to 1 radian when this length, this arc length of the circle equals the radius. So if we think about increasing the length of the arc, then we can see that that length of the arc itself is simply equal to the radius multiplied by the angle between them, because we have defined the angle to be 1 radian when the length of this arc is the same as the radius. So if we are to extend this arc some more, then we can actually see that this angle is now 2 radians. And if we extend it even more, then we can see it's just about 3 radians, or exactly 3,14 radians. So that's why we say that this half circle is actually pi radians, 3,14 radians. So pi radians is about 180 degrees. It is 180 degrees. But the whole point of this was to show that the length of the arc is equal to the radius multiplied by the angle. So here we can see that this is our radius length, dr, and our angle is d theta. So the length of the arc is r d theta. So that's r d theta. So we can see now that we have everything that we need to compute the volume element. We can just take length times the breadth times the height. The height is still, of course, z. There's no change in variables there. So what is our volume element? It's just simply r dr d theta multiplied by dz. Length times the breadth times the height. So of course the volume is simply just the triple integral around any region of r dr d theta dz. We can illustrate this in a basic example, and that example is we have some kind of plane figure here. This figure is basically the first octant. So in the Cartesian plane we would have 4 quadrants, 1, 2, 3, 4. So in 3 space we would have 8 quadrants. So each one is called an octant. So the first octant, we're considering just the first octant. We're saying that this figure is bound in the first octant, where x, y, and z are all positive. And what we're considering is the cylinder x squared plus y squared is equal to 4, and also intersecting with the plane z is equal to 6 minus xy. So we can see that this is our cylinder. We can see the shape of the cylinder, and we know that the x and the y intersections is equal to 2, because that's how we draw our circle. This is x squared plus y squared is equal to 4, and we know that it intersects everywhere at 2. So we have the shape of our cylinder. So now the other thing we just need to take consideration of is the other plane that's bound by. So that's z is equal to 6 minus xy. So that would be this plane on the top. We can see that it's not distinctly a cylinder, but it has a somewhat of a parabolic looking shape like that. So this is 6 minus xy. So how do we find the volume of this particular shape or this particular figure? Well, we just do it exactly as we had done it previously. We take our volume element,
when we integrate it. The only thing we need to take consideration of is how we're integrating it. That is our boundaries. So we're integrating firstly along the z-axis, we can think about it. Where are we integrating from? We're integrating from 0. We can see that we're starting off at 0, and then we're going all the way up, and then where are we stopping at? We're stopping at the plane at which it's bounded, so that we're stopping at z is equal to 6 minus xy. So that is our z boundaries that we're integrating. We're integrating from 0 to 6 minus xy. Then we need to think about r and theta. So r is just the radius of the circle, and we can see that the radius of the circle is 2. So we're integrating from 0 to 2. We're stopping at 2. And then lastly, theta, the angle. Theta is going from 0, we can think of 0 here, and it's going all the way and stopping at the y-axis. So this is actually 90 degrees or pi over 2 radians. So theta is going from 0 to pi over 2. And what we're integrating is r dr d theta dz. So now we proceed to evaluate this integral, but we first have to convert this xy into the variables of integration. And the variables of integration are r and theta. So it's a simple matter to convert from x and y to be in terms of r and theta. We would remember that x is equal to r cos theta and y is equal to r sin theta. So 6 minus xy is simply equal to 6 minus r cos theta times r sin theta. And this is just equal to 6 minus r squared sin theta cos theta. So we can replace that. So this is now equal to the integral from 0 to pi over 2, 0 to 2, and then from 0 to 6 minus r squared sin theta cos theta. So this is a boundary of this is the upper bound. And what we're actually integrating is r. I'm just going to write the dz first. dz dr d theta. So if you're integrating first with respect to z, all this just becomes is z. R is treated as a constant first. So we would just substitute in this 6 minus r squared sin theta cos theta. So that's what we'll do now. Okay, this should not be y is equal to. So if we do that, we just get from 0 to pi over 2, 0 to 2, and then r multiplied by z, and just z is 6 times 6 minus r squared sin theta cos theta. So we can just multiply it out now while we're at it. So we get 6r minus r cubed, basically that r multiplied by this upper boundary, sin theta cos theta. And then dr d theta. So proceeding with this integration, and now integrating with respect to r, what we have is the integral from 0 to pi over 2. The integral of 6r is simply 3r squared minus 1 over 4 r to the power 4 sin theta cos theta. And of course, this is integrated from 0 to 2. And then evaluating this by substituting in 2, what we get is 2 squared is 4, 4 times 3 is 12. And then 2 to the power 4 is 16, 16 divided by 4 is 4.
and sine theta cos theta remains as is. And lastly, this is just integrated with respect to theta. And when we do that integration, integral of 12 is just 12 theta plus the integral of sine theta cos theta is just cos squared theta and of course we need to take consideration of this 4, so we would multiply it by 2. We can understand that this is true just by differentiating cos squared theta. So the derivative of cos theta is sine theta. So sorry, that's minus sine. So that takes care of the minus here that we see. And of course we have that 2. So 2 times 2 is 4. And of course the derivative of the inside function is what gives us that sine theta. And the outside function is just the cos theta that's remaining. And this is integrated from 0 to pi over 2. So what's left when we integrate this is simply 6 pi minus 2. 12 times pi over 2 gives us 6 pi, and the derivative of pi over 2 is 0, and then we substitute in that 0 again. 0 times pi is 0 times 12 is 0, and the cost of 0 is 1, and that's how we get that minus 2. So when we multiply it by 2, then we get the minus 2. So that is how we would evaluate this particular integral. So if we wanted to integrate this particular figure using normal coordinate systems of x, y, and z, what would our integral look like? We can see that we would have to integrate still as it would be with z. It goes from 0 to 6 minus xy. Now we would need to integrate with respect to y, and we have to go from 0 to y, and we stop at this function. So we need this value for this function, and we know that it's given by the circle x squared plus y squared is equal to 4. We'd have to solve for y. So y is equal to the square root of 4 minus x squared. So we'd have to integrate from 0 to the square root of 4 minus x squared. And then lastly, we'd have to integrate from 0 to 2, dx, dy, and dz. So we can see that this is a much more difficult integral to actually evaluate if we were to proceed with it. It's actually longer to do it this way than it is just to use cylindrical coordinates. So using cylindrical coordinates has actually made it easier to evaluate this integral. We're now moving on to another change of variables. We're now going from the normal coordinate system x, y, z to that of spherical coordinates. Spherical coordinates is somewhat different from what we have looked at so far. There was some familiarity with cylindrical coordinates because it involved polar coordinates. The r and the theta was something that we can recall. Spherical coordinates is a bit different, and the change of variables might not be something one would be entirely familiar with. So from x, y, and z, we're instead moving to rho, theta, and phi. So what is this rho, theta, and phi, and how do we actually make that conversion? Spherical coordinates is generally used when there is a point of symmetry. So we can think of a sphere and everything is symmetrical about a particular point. That is, if we think about the sphere that's been drawn here, we can see that everything is symmetrical about the point of origin. So that's what is meant by point of symmetry. And we find that when we convert an integral to this particular coordinate system, it's actually much easier to integrate. All that we need to do is understand what this transformation is, that is the transformation of the variables, and understand how to set up the integral. So let's look at what these variables are in spherical coordinates and how do we go about deriving them or understanding how they come about. So let us have this sphere in the x, y, z plane, and we're going to now define what each of these variables mean. So firstly, we had this rho. You remember that instead of x, we're now going to have rho. So what is rho? Well, rho is the distance from the origin to our point. So our point is on the sphere. We can think of it as being on the outer edge of the sphere, and the distance from the outer edge of the sphere to the origin is called rho. So rho is here. We can just write it, and we can just understand it's the distance from the origin to our point. And then we have theta. So theta remains somewhat as it was from cylindrical coordinates, but instead of the angle to a point, it's actually the angle between the projection of the point. So what I'm saying is, if we have this point, and then we project this point on the xy plane, and then we define some other variable, maybe r to be the distance from the origin to the projection of the point, and the angle theta is the angle between the x-axis and r. So there is a difference here now between r and theta. There's a difference between r and rho. Rho is the distance from the origin to our point on the sphere, whereas r is the distance from the origin to the projection of the point on the xy plane. That's very important to note. So lastly, what we have is just the angle between the z-axis and rho. So we're creating a new variable there. This is the angle between our point, rho, the distance between the point on the sphere and the origin, and now that angle between the z-axis. So that is called phi. So I'll write it here, phi. So these are our three variables, rho, theta, and phi. So how do we do our conversions now? How do we convert between x, y, and z, and rho, theta, and phi? So let's draw this triangle, okay? So the first thing we need to understand is that we have a right angle triangle. So that right angle triangle is rho, r, and z. So there's our right angle triangle here. Rho is the hypotenuse, r is on the xy plane, that's the base of the triangle, and z is the height of the triangle. So we can draw it like this. We have rho, we have z, and we have r. And this angle here, this is actually phi. So we're saying that this angle here is phi. Remember, in geometry, there is something called alternate angles. So if this angle here is phi, then this angle here is also equal to phi. You can see that it makes an inverted N shape. So that angle is equal to that angle. Okay, so now we can just write our normal trigonometric ratios. If we take cos of phi, we can see that cos of phi is equal to z over rho. So that means that z is equal to rho cos phi. Z is equal to rho cos phi. So what else? Now we can think about the projection on the xy plane, because we need to move from x and y to that of rho, theta, and phi. So there is an angle that's formed on the xy plane. We can understand that quite easily. There's a right angle triangle here. And we have y, so the distance between that point and our projection is just y. And the distance between our projection of the point to the y-axis is simply x. That's y and that's x. So if we draw this triangle, we'll draw it here. We can see that this angle is theta, and then we can see that the base is x, and we can see that the height is y, and r is as it is. So this is our triangle that we used to, and we can simply evaluate x and y as we are done with cylindrical coordinates. So we can see that x is equal to r cos theta, and that y is equal to r sine theta. But there is a problem here, and that problem is that we are not working in terms of r anymore. R is not the variable with which we're going to be converting to. Instead, it's phi. Phi is what we want. So we need to move between r to phi. And how do we do that? Well, we can just use our first triangle that we have done here. And it's a simple matter just to see that r is actually rho sine phi. If we just take sine of phi is actually opposite of our hypotenuse. That's just r over rho. So r is equal to rho sine theta. So we can do our conversions now. We can simply see that x is equal to, we substitute in rho sine theta for r. So x now becomes rho sine theta multiplied by, instead of theta here, it should be phi. My apologies. So r is equal to rho sine phi, and then lastly cos theta. Then we would do y. So y is equal to r. So we write rho sine phi and sine theta. So that's done. We can now convert between all our variables. Everything is known. If we have a coordinate x, y, and z, how do we convert to rho, theta, and phi? Well, we can see everything. Z is equal to rho cos phi, x is equal to r cos theta, and y is equal to rho sine phi sine theta. So everything is known. All the conversion variables are known. So the last thing that we need to do in order to be able to evaluate is simply find the integrals. And as it was the case with everything we've done so far, we just need to take a volume element. And the volume element will look something like that. Now we need to find the volume element like that. We will just draw that out separately on another graph. So now what we're going to do is find the volume of a plane figure using the coordinates that we had just described. That is spherical coordinates. So we took this point on the sphere and we have now expanded it to be a volume element. We're now going to label each of the sides of this volume element in terms of the variables that we had just defined. So we saw that rho was the distance between the origin to the point on the sphere. So if we have a differential change in that point, then that length is d rho. So I'll just repeat that one more time. We have the point in the sphere, and if we have a differential change, then that must be d rho. It's just as how we had dr. So rho is actually the radius of the sphere, and this differential change is d rho. So anyway, we also saw that the angle between our point and the z-axis was called phi. So this angle here of this differential element is actually d phi. So what that means is that if we have a radius, so the origin to the point on the sphere, and that's rho, it means that this little arc length must be rho d phi. So I'll just write that here, rho d phi. Just as we had r d theta, we have rho d phi. So I'll just write that here. We have our little element, that's d theta, that's r. This is r d theta. So this has changed somewhat now. So here we have d phi and we have rho. So that must be rho d phi. So lastly, we have our length of this volume element. We have the breadth of the volume element. So we now kind of need like this height. Sorry, we have the height of the volume element. We also have the length. We just need the breadth. So we need this part here. So that's what we need. And how do we get that? Okay. Well, if we think about it, we took our projection on the xy plane of a point, and then we saw we had r. That was what r was. And then we also saw we had theta here. So we can think of this on the top as well. So that length is r, and the angle is actually theta. So here we have d theta, and here we have r. So the length of this, sorry, that's a poorly drawn r. So let me rewrite that r again. So it means that this length is actually r d theta. However, we don't express anything in r anymore. We saw just now that r was actually equal to phi, r was actually equal to rho sine phi. So we do this change of variables. So that's actually equal to rho sine phi sine d theta. So now we have everything to compute our volume element. So dV is equal to, firstly, the length, breadth times height. So firstly, we have d rho, okay, multiplied by rho d phi, multiplied by the width, which is actually rho sine phi d theta. So I'll just write everything. We have rho multiplied by rho. So we have rho squared. Then we have what? We have this sine phi. Sine of phi. And what's left is d rho, d phi, and d theta. D rho, d phi, and d theta. So our volume is just the triple integral of this particular function. It's the triple integral across some region of sine phi, rho squared sine phi, d rho, d phi, d theta. We can illustrate the use of spherical coordinates to find the volume of just a hemisphere. A hemisphere is just half a sphere as has been drawn here. So we find the volume. We can see that it's simply just the triple integral, as we have done before, of rho squared sine phi d rho d phi d theta. It doesn't matter in which way we write the order of integration. What does matter is how we define our boundaries. So we can just give it an arbitrary variable, that is the radius of the sphere. We can just say that the radius of the sphere is c. So phi is actually going from 0 to c. So the first boundary, which is rho, it's going from 0 to c. Then we can perhaps think of, we can look at theta, for example. Okay, let's integrate with respect to theta. So let me just reverse this order of integration here. Let's go with theta first and then phi. So theta, as you would recall, is the angle between the x-axis and whatever point we're considering. And we can see that it's actually a full circle. Okay, it's a full circle. So theta is actually 2 pi. So it's going from 0 to 2 pi.
And then lastly, we think of phi. Remember what phi is? It's actually the angle between the z-axis and the plane figure. So you can see that actually phi is actually going from 0 to pi over 2. Pi over 2 and then rotated 360 degrees. So pi over 2, that's what phi is, this angle, and then rotated 2 pi radians or 360 degrees. So that's why we go from 0 to 2 pi, that's this full circle here, and 0 to pi over 2, that is the angle between the x-axis and the radius. Sorry, the z-axis. So now we can simply just evaluate this integral. So firstly, we integrate rho squared. The integral of rho squared is just 1 over 3 rho cubed. So let's just write our outer integrals, 0 to pi over 2, 0 to 2 pi, and the integral of rho squared is 1 over 3 rho cubed, and this is just integrated from 0 to c, and then we have d theta, d phi. All we do is we just substitute in c. Sorry, I missed out a sine phi here. So let me just write that. Sine phi d theta d phi. I'll just drag the screen across so you can see it. So now we just proceed with our integral as you would normally do. So the integral of in theta is just everything else remains constant, so we just write theta. So we have the integral from 0 to pi over 2, and the integral of all of this is just theta because everything else is constant. So we substitute in c here, and we have 1 over 3 times c cubed. And then the integral of d theta is just theta. And then theta is going from 0 to pi over 2, 0 to 2 pi. And lastly, d phi. Or rather, sine. I keep forgetting the sine, the phi, sine of phi. Sine of phi, d phi. So all we do is we just substitute in 2 pi here. So when we do that, we get 2 over 3 pi times c cubed. Let's just write that out. 0 to pi over 2. We substitute in 2 pi into theta, and then we bring it out, so we get 2 over 3 pi times c cubed, sine of phi d phi. So lastly, all we do is integrate sine of phi, and when we do that, the integral of sine is minus cos. So we have 2 over 3 pi c cubed times the integral of minus cos, times minus cos phi from 0 to pi over 2. And of course, the cos of pi over 2 is just 0, and the cos of 0 is 1. And you put minus because because the lower boundary, so this becomes positive 1. So what we're left with is simply 2 over 3 pi c cubed. Most people would remember, if they have studied maths at various levels, that the volume of a sphere is just 4 over 3 pi r cubed. You can see that it's kind of the same formula, but we looked at a hemisphere, we looked at half a sphere. So if we just divide this by 2, then we get 2 over 3 pi r cubed, which is actually what we had
just done here. So this just illustrates the point that we can very much easily evaluate complex integrals with complex equations if we can actually just do this transformation. Because think about if we had to actually do this in terms of x, y, and z. You would remember that for a sphere, it's described by x squared plus y squared plus z squared is equal to c squared. We would first have to integrate with each specific variable, and you can see that it's much more challenging to do it like that. So if we just do this transformation, we can do it quite easily. So this was a sphere of constant density. If we have variable density, then we have to take that into account as well, because instead of just having rho will be a function. So the density would be a function. So if we have to compute the mass, the center of mass, the moment of inertia, it would be a more complex looking integral, but the principle remains the same. All that we would need to change is basically the order of integration. If we're integrating a hemisphere, then we're integrating theta from 0 to 2 pi. If it's just the top half of the sphere, then we're integrating phi to be between 0 and pi over 2.